Good morning, good afternoon, good evening. Thank you all for joining this morning. Welcome to your day 3 of the 3-month hands-on certification program in Pharmacometrics and PKPD modeling using RS and LME. So we are in the module 1 of this workshop. And again, we have a great participation like always. I know some of you have had dialed in very early as 8:30 a.m., which is half hour before the start of the workshop. Thank you again for being diligent and being present and being early to the workshop. I acknowledge you all who have been diligently working through all the homework assignments, have also looked at the previous workshop videos as well as slides. And of course, I also acknowledge all those who have taken on being group leaders and are supporting the various members in your group in expanding their knowledge and helping them through the homework assignments. Thank you so much. And today we have Dr. Gozi back with us, and he will be covering more on the topics. And I know that some of you have looked at the homework assignment that was sent to you last week. And I also understand that the homework assignment may have been an extended reach. However, that our plan was that you start thinking in that direction. And today, Dr. Gozi would actually be covering some of those concepts, so you would be able to address the homework assignment questions, as well as you will get additional assignments after today's workshop. And if you have not already done so, please subscribe to Project Dontabhaktuni's YouTube channel. All these programs and workshops are recorded and we post them on the YouTube channel. Again, the day 1 of the workshop is already on the YouTube channel. The day 2 should already be there. If it is not there, it should be getting in sometime today. And we will try to keep on top of giving you all of these recordings as soon as possible. Thank you again for being here. And I would hand over the baton to Dr. Gozi to bring us back into module 1 and discuss more of the PKPD concepts.
Okay. Okay, thanks a lot. Okay, let me see. Okay, before we start, I would like to make a small announcement about the homework. I gave you a homework about a question about the likelihood. I don't want you to do anything about it because the answer is not so easy as I thought at the beginning. Then no need to do that. You just need to do the 7 question about the PKPD. And you already covered that material, then you can really start now. Now, what I'm going to do now, usually when I'm talking about categorical response, candidate and time to event, it's more a discussion that I have with the students. But obviously here it's more difficult to do that way. Then I will pretend that we are talking together and that we are discussing. Then the first thing that we need to ask ourselves, and remember, don't do the question about the likelihood. Arunash is going to send you a notice for everybody. That will be important because I don't want you to spend time in something that basically the answer is not trivial at all. Then what we talk about continuous response so far, if you remember, the PK was continuous. Yeah, it's an observation, it's a concentration. The PD, the pharmacodynamic, when we talked about the effect that we modeled with a direct or indirect response model, we are talking about continuous response. Now, what's the main difference between continuous and non-continuous response? This is a very good question. And why is it so complicated to handle and to understand and to feel non-continuous response compared to continuous response? The answer to this is very simple. When you talk about the continuous response, just take an observation. Suppose that you observe the concentration, you record an observation, you record the concentration, and let's say that the concentration is equal to 55.5. Then you are going to assume a model, it's a continuous model, and you are going just to see, okay, if I'm putting some parameters in my model, do I get at the time where I observe my response, do I get something that is near the observation? Let's say 55.5, do I get something near that? Now, because it's a model that it's continuous, you are going to get an answer that it's continuous. You're going to get, for example, 57. Then when I look at 57 and I compare my prediction, which is 57, and my observation, which is 55, immediately I can have a feeling that I'm near, that basically my model is behaving the right way, and maybe the parameter that I plugged in that gave me 57 is a good parameter. Now, what's the problem when we are talking about continuous response? When you are talking about continuous response, you observe now, well, let's just talk about the categorical response. What is a categorical response? The simple example is just talking about the pain model. You have patients that take the drug, that's the PK part, and then with time you just want to see if the drug relieves the pain. Then usually people are going to start with a severe pain, and hopefully are going to go from severe to moderate, moderate to mild, and mild to no pain at all. You assign a number which is completely arbitrary, and for example, you put 3 for severe, 2 for moderate, 1 for mild, and 0 for no pain. Now, I observed a number which is 3, 2, 1, and 0, but my model, it's not a continuous model. I'm going to model the probability to get any of the number, 3, 2, 1, or 0. The probability that I'm going to model it's a real number that's going from 0 to 1. Then, for example, that I have a model, and I observe a severe pain, which is 3. And then I see that the probability to get severe, it's, let's say, 70%. The probability to get 2, it's 20%. The probability to get a mild pain, it's 10%. And then the rest, what is remaining, it's no pain. I model a probability, which is between 0 and 1. But I observe a number that can be 0, 1, 2, 3. Then we are talking about 2 different dimensions. Then if I plot, for example, the probability to get any of the pain level, and I compare with my observation, I cannot visually, I cannot intuitively understand if the parameter I plugged in my model that gave me the probability to get severe pain means that really that's the best parameter that explains my data. And remember that when I have a continuous response, if I have 10 patients and all the 10 patients have a prediction that it's need observation because they share the same dimension. Observations 55, prediction 57. We are talking about basically the same kind of dimension. We can compare directly the 55 with the 57. When you are talking about categorical response, you are going to compare probability with a sample from that probability distribution. When you have categorical response, that's what you are doing. The truth is that you do the same thing with continuous response. We don't feel it because the model itself give me a number that shares the same dimension as my observation. And that's the main difference. Now, we want now to model the probability. Then in order to model the probability to get any of the pain level, I need to remember what is a probability, what are the constraints that I have in a probability space, and what should be the strategy to build a probabilistic model when you have categorical response. Okay, then that's what we need to do. Then what do we know about probability? That's where basically I have a discussion with the student. I'm asking, what do you know about probability? But now I have to do the discussion with myself because I have no other choice, because we have a Zoom meeting, meeting, and not really a course face to face. Then what do I know about probability? I know that probability should be a number between 0 and 1. Suppose that I have the level 0, 1, 2, 3, then whatever model I have for the probability to get 0, 1, 2, 3, whatever I'm doing, I need to make sure that the probability to be 0 is between 0 and 1, the probability to be 1 is between 0 and 1, same for 2 and same for 3. Now, what is the cumulative probability? The cumulative probability, for example, if I'm talking about the cumulative probability that includes the level 0 and 1, it is in fact the probability to get 0 or the probability to get 1, which is basically the probability of getting 0 plus the probability to get 1. This is called a cumulative probability. If, for example, I'm starting with the severe pain, then I have the probability to be 3. Okay, this is called the marginal probability. Then if I'm talking about the first level of cumulative probability, I'm asking myself, what is the probability to get 3 or 2? Now, I know that the probability to get 3 or 2 first must be larger than the probability to get 3, but also must be between 0 and 1, because the cumulative probability should be also between 0 and 1. Then I have the next level of cumulative probability when I ask myself, what is the probability to get 3, 2, or 1? Again, this cumulative probability should be between 0 and 1, and should be larger than the probability to be between 3 or 2, or the probability to be equal to be at level 3. These are basically basic probabilistic rules that we need to always be confined within. The last constraint that we need to obey by is that the sum of all the probability must be equal to 1, and also that probability can never be negative. I told you, because it has to be between 0 and 1. In other words, whatever I'm doing, my model must have the constraint that the probability to have a level 0 or 1 or 2 or 3, the probability to basically equal 0 plus probability to equal 1, 2, or 3 must equal always to 1. If the probability to be in severe pain is 70%, 2, 20%, 1, 5%, then obviously 0 is also 5%. It can never be. Now,
Serge,
yes.
This is Karuna here. Just a quick question. And again, this is for my understanding as well, right? So the 5 different levels could have been A, B, C, D, right?
Yeah, it's completely arbitrary.
Right. So just so to clarify, and so that the participants don't get confused, the 5 different levels that Dr. Gozzi is talking about are not connected to the 0 or 1 of the probability. The 0, 1, 2, 3, 4 that are discussed here could be A, B, C, D, E, F. Okay.
Yeah. Okay.
So
okay, very fine. It's completely unrelated. It is common to use integers for each level. That's usually what we do, and also we usually use 0, 1, 2, 3. But you could use A, B, C, D. You could use 0, 2, 4, 6, 8, and it has nothing to do with the 0, 1 of the probability that we are talking about. Okay, that's a good point, and it's very important to understand that.
Thank you, Serge.
Okay, you're welcome. Then now let's just talk about some functions that are very important. And the first function, now remember that whatever model I'm talking about, it's a probabilistic model. Then whatever function I'm putting, I should be sure that the probability is between 0 and 1. And that's what we use in transformation that it's called inverse logit. And this is basically the function. I don't know if you see my cursor. If you see my cursor, that's great. I guess that you see it. You can see I logit x is equal to e to the x plus 1 plus e to the x, where x can go from minus infinity to infinity. Let's just look at this equation to see what's special about this equation. When x is negative and going to minus infinity, then you can see that you get e to the minus infinity, which is basically 0. It's converged to 0. Divide by 1 plus something that converges to 0, then it's 0. Then on one hand, when x is very, very negative, it converges to 0. Now, if x is really positive and very large, then e to the x will be larger than 1, and the 1 cancel, and you get e to the x divided by e to the x, which is 1. Then what you can see is that if you constrain the x, whatever is x, to be between minus infinity to infinity, in other words, without any constraint, the whole space, the whole dimension space, then basically automatically I log it of any function that can go from minus infinity to plus infinity will go from 0 to 1, which is good because that's exactly the constraint that we have for probability. Then this gives me an idea. This gives me that instead of writing the probability model using, some function that I know where to start, why not using a function that includes I log it? And in the x, I'm going to put whatever I want, anything that I want. I mean, we're going to talk about that. And I know that whatever I'm putting, as long as it's going from minus infinity to infinity, I know that I will cover the whole range 0 to 1. Now, let's just take the example with 4 categories, 0, 1, 2, and 3. If you want no pain, mild pain, moderate pain, severe pain, as I will mention, the 0, 1, 2, 3 has nothing to do with the probability that go from 0 to 1. Okay? Then I have 5 categorical levels, and I want to build a model. Okay? Then we already talk about that. The main difference between continuous and non-continuous. Continuous, it's easier. You have goodness of fit. You see what you have. With categorical response, it's more difficult to see what you have. Then we need to be smarter, and we need to define we need to go by a cookbook that I've been teaching for years to my students, and that hopefully help to build a model with categorical response. I'm giving you just I'm just giving you here the concept. And once you are going to practice that with examples, then you will understand better. Obviously, because I'm not teaching RNLME, it was very difficult for me to give you example using a software because I don't have I'm not teaching the software. Okay, then again, we have 4 levels, 0, 1, 2, and 3. Okay, and suppose that, again, we are talking about categorical response, and we have a drug. Then we have a PK part, which is continuous, which is C, which is the predicted concentration. Okay, and we assume, hopefully, that the exposure is going to decrease the probability to get high level scores. Then the question is how we are going to build a simple model that will enable us to fit the model to the data. And again, this is just introduction to categorical response, the concept and nothing more. I do not explain you the cookbook, how to really deal with real examples, because I don't have really the example here. This will come later on. And by the way, when we are finished with the workshop, I will be happy to help people with real examples that will use the Phoenix modeling language that I know very well. Then again, the probability should be between 0 and 1. Then obviously I'm going to associate the probability to my I log it operator. It's called an operator. And I'm going to say that P is equal to I log it of X, because I know that the probability is between 0 and 1. And I know that I log it X is also between 0 and 1. Now let's just play a little bit with some functions that it's very important to know about it. Inverse logit, the inverse of an operator, for example, if I'm taking exponential, I know that the inverse of exponentials is logarithm. We know that when you apply the inverse operator on an operator, they cancel each other. Then if I put exponent logarithm x, it's x, because exponent and logarithm are inverse operator. The inverse operator of the I logit is called the logit. By definition, the logit of the I logit of x, because logit and I logits are inverse operators, they cancel each other, then it's equal to x. Then basically, but I logit of x is p, the probability. Then logit, then you can see that logit of I logit x and I logit x is p, is equal to logit of p. I logit and I logit cancel, and you get logit p is equal to x. It appears also that the logit of a probability is equal to logarithm of p divided by 1 minus p, which is called the log of the odd ratio if you are familiar with these terms. And remember, x going from minus infinity to infinity. All this is just to tell you that what we can do is to write the model in the logit domain, because we know how to go from the logit domain to the probabilistic model, to the probabilistic domain by just using the I logit. Then just it's like a game that we use all the time. But when you are going to work with categorical response, many times you are going to see the logit of the probability to get level 3 is equal to something. The logit of the probability to get level 2 or 3 is equal to something. The logit of the probability to get to have a level 1 to 3 is equal to something, rather than directly the probability to get a level. That's basically what you are doing. Now, let's just take a simple example. Let's start with the high level, which is basically severe pain, which is basically 3. We have the level 0, 1, 2, 3, remember? And I want to write an equation for the probability to get level 3. I'm going to assume that basically inside the I logit operator, I have a linear function of the concentration, straight line if you want, okay? Then I'm going to assume that I have the probability to get level 3 is equal to I logit of A, that's called the intercept, plus B multiplied by C, where C is the predictive concentration that you can get that from your PK model, okay? Now, then the program is going to estimate A and B, and C will be estimated by the PK model. Then everything is good here. What I know is that the probability always will be 0 and 1, and basically I need to estimate A and B. Now let me stop 1 second, it's because we need to be careful. I just gave you A plus B multiplied by C, and then you should tell me, yes, okay, what's happened when basically the C increase forever? It could be a problem because if, for example, if the B is positive and A is positive and C is going to infinity, then basically what we are going to see is that the probability is basically going to 1, which means that basically, I mean, if B is positive, then it means that everybody is going to have a severe pain. And if B is negative, which is more in our case, because we want to have people, when the drug to remove the severe pain, if B is negative and C is going to infinity, it means that the drug is going to work on everybody and everybody is going to have the severe pain removed. In practice, instead of a linear model, sometimes we can have a saturation like a Emax model. It would be A plus B multiplied by C divided by C divided by C plus DC50, which means that even when the concentration is going to infinity, it doesn't mean that all the patients are going to have the severe pain removed. But just to understand the concept, I'm going to assume a linear model. In practice, you must be careful, but choose usually a saturatable model if you can. Okay? Now, let's just play with the definition here. I have a model for the probability to get in level 3. And now let's just try to understand what we have here. If I apply the logit operator on my probability, I'm getting logit of the probability to get severe pain, which is y equal 3, is equal to logit of I logit of A plus B plus C is equal to A plus B multiplied by C. Now, then you can say, okay, then why not doing the same thing with the probability to get level 2? Now I have a problem here. If I would write the probability to get level 2, y equal 2 is equal to I logit of, let's say, D plus E multiplied by C, and I do not link that probability to the probability to get level 3, then maybe the sum sometimes is going to be larger than 1. And I cannot have that. Then the trick to make sure that the probability to get level 2 is defined in such a way that it's always larger than 0 and less than 1, it's just rather than defining the probability to get level 3, probability to get level 2 equal to something, just to say, let's just write an equation for the probability to get level 2 or 3, which is probability to get y larger than or equal to 2. And now let me show you what I did before. Remember that before I defined the probability to get in level 3 in the logit domain. Remember that I can use the logit domain as I mentioned. Sorry. The probability to get level 3 in the logit domain, I defined this as a plus b multiplied by c. We just did that. Now I'm going to define the probability to get level 2, not directly, but I'm going basically to write an equation for the probability to get level 2 or 3, which is y larger than or equal to 2, is equal to a plus b multiplied by c, which is basically what I just got before. And I'm going to add a number that is positive. It appears that if I'm adding a number that's positive in the logit domain, so the probability will be larger than the corresponding probability to get level of 3. In other words, when I'm writing the probability to get 2 or 3 in the logit domain is equal to what I had for the probability to be in level 3, but I'm adding a positive number plus d, I'm sure that this probability, which is a cumulative probability, will be larger than the probability that I just defined before, which is exactly what I need, because the probability to get level 2 or 3 must be larger than the probability to get level 3. And again, a plus b multiplied by c must be the same, but again, you can put here saturation, you can put whatever you want here. What the red part, you have complete freedom. The d that you add must be positive. Now you understand the trick. Then I will never define directly the probability to get level 2, but I'm just going to define the cumulative probability. Then let's do the same with the last probability that is remaining, because I don't need to know anything the probability to get level 0 because I have 1 degree freedom. If I know the probability to get level 3, 2, and 1, I know that the probability to get level 0 is equal to 1 minus the sum of all the other probability. Then if you have 4 levels, you just need 3 equations. Again, if you have 4 levels, you need 3 equations because it's 1 degree of freedom. Now let's use the same trick to define the probability to get level 1, 2, or 3. 1, 2, or 3, it's a probability that my level y will be larger than or equal to 1, because larger than or equal to 1 is 1, 2, or 3. 3 is the maximum level. Then again, this is equal to what I had for the probability to be level 3. Then what I add the d that gave me the probability to be in level 3 or 2. And now I'm adding e, which is also larger than 0. Then now I wrote basically 3 cumulative probability. The first one that is basically the marginal probability, because I start with that one. I always like to start with the highest level. Okay, but again, you have completely full degree of freedom to do whatever you want. I like to do what is called to use descending probability. I'm starting with probability to be in level 3, and I'm adding 2 or 3, then 1, 2, or 3. Now, what is good about that? All the cumulative probability are between 0 and 1 because of the logit transformation. The probability to be in level 3, it's less than or equal to the probability to be in level 2 or 3, and same thing, the probability to be in level 2 or 3 is basically less than the probability to be in level 1, 2, or 3, which is basically also a constraint. And now we define everything, and the program hopefully is going to estimate the A, B, D, and E. Now, how I can find what's the probability to get in level 2 when basically I define the cumulative probability? Obviously, this is easy. I'm starting with the first probability to be in level 3 that was put in the logit domain. Then in order to get the probability to be in level 3, I just need to apply the I logit operator and the logit probability to right equal 3. And I'm getting probability to get level 3 is equal to I logit A plus B multiplied by C. Now, what is the probability to get level 2 or 3 is equal to I logit of A plus B multiplied by C plus D. But that's the probability to get level 2 or 3. Therefore, what's the probability to get level 2 is equal to the probability to get level 2 or 3 minus the probability to get level 3, which is equal to I logit A plus B multiplied by C plus D minus I logit A plus B multiplied by C. Then now you understand that you can always go from the cumulative probability to the marginal probability, which is basically what you want to calculate at the end of the day. And you do the same thing with the probability to get level 1. In other words, once you define your model in the logit domain using cumulative probability, you can, when you are done, you can calculate the probability to get any of the level. And again, once you know the probability to get level 3, 2, and 1, the probability to get level 0 is equal to 1 minus the sum of all the other probability. Now, one of the topics, and again, I don't want you to work on the likelihood equation. And again, I want to make sure that you don't work on that. But it's important to understand that when you do optimization, you need to define what is called an objective function. What is an objective function? It's like a distance. As an example, one of the objective functions that you use all the time when you do not talk about population approach, for individual approach, it's basically the least square, which is a distance. In other words, you need a tool that allows you to decide what is better. For example, if I have a categorical response, I have the A, B, D, and E. If I put A equal 1, B equal 1, D equal 1, A equal 1, I need to calculate something. And from this something, if I change A, B, D, and E to see what is better, the A equal 1, 1, 1, 1, or for example, A equal 1, B equal 0, D equal 2, and E equal 3. You do that when you define what is called the likelihood associated with a specific observation. For categorical response, it is just a probability to have obtained that observed category. In other words, if you observe a category of 3 for a specific individual at a specific time, and again, it's just one individual, and then for that individual and that observation, you start with A equal 1, 1, 1, A equal 1, B equal 1, D equal 1, D equal 1, for example. And then basically you can calculate the probability because the probability is given here. You know, we have the probability to get level 3, it's A plus B multiplied by C. Then you get observation equal 3. Then you can say, okay, with the A equal 1 and B equal 1, and I know the concentration at that time with the dose that I gave, then I say that's my probability. Then that's my first patient at the first observation. Then later on, again, you observe what's the pain after, let's say, 10 hours. Then again, if the level is 3, you say, okay, then the likelihood is in that case is a probability. When I use A equal 1 and B equal 1, then the probability is given by A plus B multiplied by I logit of A plus B multiplied by C, where C is the predicted concentration, A equal 1, B equal 1. Then I can calculate then the probability associated with the level that I observe for that patient at each time. And I multiply the probability. And then I'm doing that for each observation. And at the end of the day, I have basically, I compute all the probability for that specific value of A, B, D, and E that I told you. Now, what is more complicated with the population approach is that basically first I have many individuals. And also, each individual it doesn't have one specific value A, B, D, and E, but it could have basically many values that explain the data. For example, A could be one which is the best value for A, but he has a certain probability also that 0.1 could explain the data. Then basically the program is doing something very complicated, which is integration of the likelihood, and I don't want to go too much into that. What you need to know is just to write the likelihood associated with a specific observation, because that's what you will need to write when you are going to use R and LME for categorical response. If your observation is 3, the likelihood is the probability to get 3, which is basically the I logit of A plus B multiplied by C. If basically you get an observation is equal to 2, then the likelihood is the probability to get 2. And the probability to get 2, it is basically I logit of A plus B multiplied by C plus D minus I logit A plus B multiplied by C. Then you can see that it's very easy for you. I'm just going to shut down my phone. If you know the level for each patient at each time, you can write just the likelihood associated to each of the observations. That's the only things that you will need. All the rest is done by the software. And I'm pretty sure that when you do optimization, R and LME or Phoenix and LME, it's exactly the same thing. The only difference between the two software, it's how you can define a model, etc., how you do plots, etc. But both are going to use the same logic. Any of the software is going to use the same logic. If you use non-man, Monolix, Phoenix and LME, etc., sAdapt, adapt, everybody is going to ask you, write the equation for the likelihood. Then when you are going to write your model, you are going to say the following. If my observation equals 3, then the probability to get 3 is equal to I logit of A plus B multiplied by C, if that's your model. If my observation is equal to 2, you are going to write the equation for the probability. If my level is equal to 1, you are going to write the probability, etc., etc. And then you are done. Then you start, okay, in practice, how you handle initial estimate, all this kind of stuff. I cannot talk about now because I'm not teaching you the software. But that's basically the idea. Now, we are done now with the categorical response. And now to confuse you even more, let's just talk about some other kind of data. And let's just try to understand together with 3 examples, what kind of data we have. Remember what Aruna just told you. When we are talking about pain level, 0, 1, 2, 3 is completely arbitrary. And what does that mean, arbitrary? Something very simple that even in the first grade, people understand that. When it's not arbitrary, 0 plus 1 is 1. 1 plus 1 is 2. 2 plus 1 is equal to 3. Because that's not arbitrary. That's basically how the basic mathematical rules work when we are talking about values that are linked one to the other. When you have categorical response, 0 plus 1 is not 1. 1 plus 1 is not 2. It's not relevant because you basically define 0, 1, 2, 3 completely arbitrary. Now, why I'm telling you that is because I want to talk now about some different examples and just try to better understand the kind of data that we have. If I observe direct levels, it's a continuous response. Usually it's a continuous response at the precision level, 55, 57, 56.8. In theory, I could get any precision that I want, depending on my assay. And then we say that it's a continuous response. In a continuous response, 5.5 plus 5.5 is equal to 11. 2 multiplied by 3 equals 6. Okay? That's basically a continuous response. Let's just talk another example, disability level. None is called 0, mild is called 1, and severe equal 2. But as Arina mentioned, I could just reverse that, and I could define none is 2, mild is 1, and severe, severe is 0. Or I could say none is A, mild is B, and severe is C. Okay? Whatever basically I want. Remember that the reason to use 0, 1, 2 is that the software required that the level must be integer. And also in theory, I can put A, B, C, but when you are going to analyze the data with the software, you still will need to associate to each level an integer because the program doesn't understand A, B, C, okay? In theory, you could put A, B, C. In practice, you must be put an integer. But again, disability level, like pain level, the levels are completely arbitrary and the rules of addition and multiplication do not apply, okay? Then the first example is a continuous response. The second example, it's a categorical response. And let's just take another example. Every month, patients go to the clinic and through new technology, the doctor detects the number of cardiac events the patient had during that month, okay? The number, remember the word number of cardiac events the patient had during that month. Suppose he had 4 cardiac events in the first month and 2 the second month. Here, 4 plus 2 equals 6. I'm very good in mathematics, you can see. Then 4 plus 2 equals 6, because really 4 cardiac events plus 2 in the second month, total in the first and second month together is 6. Then the total number of cardiac events is 6 over the 2 months. The number is an integer because you cannot have 1.5 cardiac events. You can have an average of 1.5 cardiac events, but every time that you have an observation, it should be a positive integer or 0, or positive up to 0, but never negative. Then this is called count data. And that's the topic of our today's discussion, second part. In the count data, all the numbers are either 0 or positive integer, and the rules of addition and multiplication apply. But you cannot have a real number like 1.5 or 2.5. Only the average can be a real number, but not the observation. Then when we have basically count data, the number must be either 0 or positive. Now the question is that basically, how can I define a model that will allow me to now calculate the probability to get the observed number of count that I got? For example, here, when I'm talking first month, I have my first observation, I see a 4. And second month, it's a 2. And the question is basically, how can I write a model that it's linked to exposure that quantify the probability that I would have got my 4 observed cardiac events on the first month and my 2 cardiac events on the second month. The idea here is that we believe that the cardiac event is the reflection of sudden shift from no event, no cardiac event to event. That's basically the question I'm asking. Basically, what's happening is really suddenly that I'm shifting from a cardiac event to no cardiac event, or maybe there's something in the background. There's an underlying process that it's continuous, that's happening, and this is called basically the hazard rate. In other words, the hazard rate notion telling you, you know, every second, there's a certain probability to get an event. And every second I'm checking, did I get or did I get? And then basically, if I have a model that defines the hazard rate defines the number of events per unit of time. What does that mean? If, for example, I have, let's say, 0.01 event per day, what does that mean? It means that I have a very few, if for example, I have 0.01 event per day, now multiply the 0.01 by 100, then basically it means that basically I have in average 1 event per 100 days. And this gives you basically in average, it means that if I would wait for 1,000 days, then I should expect an average of 10 events. Then what's happening is that rather than modeling immediately the probability to get a specific number of events, I'm going through the concept of hazard rate. And in the software, in the RNLME, you will need to define just the hazard rate. And I'm going to see that basically that's something that we need. Then we need to define basically a hazard rate. We need to define a hazard rate. And let's just give a simple example. Suppose that the hazard rate, again, is equal to A plus B multiplied by C, where C is the predicted concentration. Now the concentration changes with time. And what the program is going to do, suppose that you want to know what's happening in 30 days. Suppose that after 30 days, you basically record a certain number of events. Let's say five. Suppose you observe 28 new events after 30 days, okay? 25 events in the second month and 35 events in the third month. And suppose that now you define a function for H, which is the hazard rate. What the program will do, it will basically calculate the cumulative number of events over the 30 days, which is the first one, okay, for the 30 days. And H is a function, A plus B multiplied by C. The program is going to integrate the hazard rate of the first 30 days, and is going to get, let's say, the cumulative hazard. It's basically the cumulative number of events. Remember that H is the number of events per unit of time. If you multiply by a time domain, you are going to get basically the cumulative number of events. And suppose that if you integrate H from 0 to 30, and you get, let's say, 27.5, cum H equals 27.5. You are going to compare the 27.5 with the 28 new event, which is good. If H has also parameters, and you would get, let's say, 10 predicted event compared to 28, then apparently the parameters are not right, and the program is going to optimize the parameter until you really have a best match. For example, one of the functions that we use here for the hazard rate, it's H is equal to H0 multiplied by 1 plus C divided by C plus C50. It's just an example. And C is the predicted direct level. And what you can see, it is basically, it's that the concentration increase the hazard rate. When C equal to 0, it's called the base hazard rate. And then basically, when you increase the exposure, the hazard rate increase. Then the program is going to estimate H0 and EC50. And the C is going to be predicted by the PK model. Then again, you will define a function in your RNLME. You are going to define, for example, a function. And in order to define correctly the function, you need to know what the drug is doing. If the drug basically increase the number of events, you are going to use this kind of model where the exposure increase the number of events, because if the hazard rate increase, so is the number of events. If the drug is going to inhibit the hazard rate, you are going to put 1 minus something, minus C by C plus C50. If, for example, you have saturation, you can use basically an Emax model or an Imax model. Then what the program is going to do is the following. It's going to take the first month's data, and it's going to try to estimate H0 and AC50 that maximize the probability to have gotten the count data that we observed. Now you're going to tell me basically how it's working. The program basically is going to integrate from 0 to 30, and is going to get a cumulative number of events. And suppose that it's getting 27.5. Then the program is going to assume that this cumulative number of events is the mean of a Poisson distribution. And again, you get 27.5 as the mean. And then it's going to say, okay, if my mean is 27.5, what is the probability to have gotten observed number 28 events when basically the average is 27.5? If you know the mean of a Poisson and you know how many events you observed, the program is going to calculate that probability. Then that's your likelihood. Then if my observation is 28 and I'm getting basically a cumulative number of events, which is the average of my Poisson distribution of 27.5, then the probability to have a mean 27.5 with 28 observed events, it's called basically the likelihood. And the only things that you will need to do is to define the hazard rate. Then you are going to define the hazard rate in the RNLME. And again, how to do it, that's basically beyond the scope here because I don't have an example, but that's the idea. If you define the hazard rate, then the program automatically is going to do the integration, and then it's going to go to the next, to the second month. Now, once I'm done with the first month, the program forget about everything, is reset the cum-H, the cum-H to 0, and they say, okay, now I'm going basically to see what's happening in the second month. Then it's going to integrate starting at 0 the hazard rate during the second month. And again, it's going to get a cum-H, let's say 29 for basically H0, a specific H0 and a specific EC50. And say, okay, I got 29. That's my average. That's basically the mean of the Poisson distribution. And then the program is going to say, I'm going to estimate what's the probability to have an average 29, to have a Poisson distribution with 29 mean, if I observe 25 events. And again, that's my new likelihood. And then you continue for it, for the same patient at each observation. You multiply the probability, okay, because all these probabilities are independent. And then you go to the next patient and you do the same thing, And then the program automatically is going to get the overall likelihood. Again, it's a little bit simplistic, but that's okay. And then it's going to say, okay, I start with a specific H0 and EC50. Now I need to shift the H0 and EC50 to something else. And then he's using some smart optimization tool to know what is the mean H0 and the variance for H0 and the mean EC50 and the variance for EC50 that basically optimize my likelihood or minimize the -2 log likelihood. That's basically the idea. And then in practice, you are going to learn that with specific example. That's exactly what I explained here. Basically, the program is going to do the optimization, and that's basically the likelihood for the count data. I just explained you that. If you get basically the cumulative number of events is equal to 2.8, that's your mean. If you observe 2 count, the probability you are going to the individual contribution to the likelihood is the value of a Poisson distribution with a mean of 2.8 and an observation is equal to 2. And then you continue, and at the end, you are going to optimize your system. What is important, and again, this is really very important, the only things that you need defined is the hazard rate. And that's the most complicated things because you need to have a lot of experience to know what kind of hazard rate to use. But again, if you will need help with specific example, I will be always happy to help you if you are students. Now, the last topic for today, it's the time to event. Then remember, we talk about categorical response. That's example, pain, disability. The number have no meaning. 1 + 2 is not equal to 3. We do not use addition and multiplication. That's categorical response. Count data, you get 4 cardiac events, 6 cardiac events, 8, 10 cardiac events in the first month, okay? And in the second month, and then in the third month. That's count data. No, let's try not to confuse and see time to event. What's different between the time to event and count data, because it's quite similar. What you need to know about count data and the difference with time to event. In count data, I'm looking at the first month. And I say, I got 2 cardiac events, but I don't know when I got the cardiac event. I know that I got in the first month. Who knows when I got the first one, the second one, I don't know. That's count data. You always, with count data, you look at the interval time interval, and you look during that time interval, how many events did you get? That's count data. Now, when we are talking about time to event, the simple case of time to event, which is the one of interest here, it's a little bit different. The people enter the trial, okay? And then when he's getting an asthma attack, he's calling the physician, he's told, I got an asthma attack. And then you record the time at which he's got an asthma attack. And let's say it was 1.2 days after starting the medicine. Then in that case, it's not like count data that in the first month, he got one asthma attack, and you don't know when. In the time to event, the most important situation case for time to event is that when he's getting the asthma attacks, you notify the physician and you record exactly the time at which he got the asthma attack. And in the data set that you are going to learn with RNLME, you will need to define what is called the sensor. And after 1.2 days in the sensor column, you are going to put a 1 because it means that you know exactly that he got an asthma attack after 1.2 days. Okay, that was basically the first example. And so again, that's the most important one. You know exactly when he got the asthma attack, and you know that he got only one asthma attack. Second example, patient B goes to the clinic 2 months after starting the medicine and is asked if he had an attack during the 2 months. The patient, remember, he got one attack and that's it. No exact time is provided, but only the fact that he got one attack. Then basically based on the same idea, this is basically count data. Then what you can see is that the second scenario of time to event include also count data. That's why you are going to see with RNLME, if it's working like Phoenix and LME, what we did when we developed the software is that we put together the situation where you can have either a case where you know exactly when you get the asthma attack, or basically you know that you got the asthma attack during the first 2 months, but you don't know exactly when. And that's called, using the time to event terminology, interval sensor. You don't know exactly when you got the attack, but you know that during the first 2 months, you got only one attack. That was the second scenario. The third scenario, again, you observe the patient for 2 months and you tell the doctor that you didn't have any attack. In that case, in the data set, you are going to put in the time column 2 months, and in the sensor column, you are going to put a 0, because it's called white sensor, which means that you didn't get an attack, and apparently you stop the trial and you are going to get an attack later on. That's called white sensor, which means that you didn't get anything yet, and you assume that you are going to get later on, but you don't know when. And that's why you call it white sensor. In other words, that the event didn't occur yet and will occur only after you stop the trial. That's called white sensor. The fourth scenario, it's like this, it's very similar to what we just talked about count data. It's also a kind of count data. Patient D comes after 2 months and tells the doctor he had one attack between day 7 and day 10. In the previous case, he started at 0, and then after 2 months, he's basically he got one attack. Then you know that it was interval sensor, it's a count data, but you know that in 2 months he got one attack. Then here's exactly the same thing, except that you have more precision about when it happened. It happened between day 7 and day 10. And then in the data set, you are just going to put a 0 at day 7, okay? Because he didn't get yet anything. And on day 10, you are going to put the time column 10, and you are going to put basically a value. Again, I don't know how what's called in Phoenix and LME, you are going to put a -1, which means that he got one event between day 7 and day 10. And we use a negative number to avoid confusion with 1, which means that it happened exactly at that time. Then again, here, it's also a count data, except that you have more precision about when it happened. The fifth scenario that you are going to learn in time to event that can happen is that patient E comes after 2 months and tells the doctor he had at least one attack on the first week after starting medication. And what does that mean, at least? At least means that he got either one attack, 2 attacks, 3 attacks, you don't know. But that means at least. And again, it's a different situation because the likelihood will be different. Because if I'm getting at least one attack, okay, then it's equal to 1 minus the probability to get no attack at all, okay? Because at least one attack, it's either 1, 2, 3, 4, 5, 6, 7, etc., etc. And then 1 minus that, it's basically what's remaining is no attack. Then the last example, it's against count data. It's basically patient F comes after 2 months and tells the doctor he had exactly 5 attacks during 2 months. And it's against count data. He started at 0, he got to 2 months and got exactly 5 attacks because we don't know exactly when he got the attacks. Then you have many examples that are the same. And all the idea here is that all the scenarios are attached, are linked to a specific likelihood that we are going just to play, that we are going to explain now. Then here, how to difference between the type of event. I already did that for you. Patient A is asked to call the physician when he suffers from a new asthma attack. He's calling 1.2 days after starting the medicine. This is a time to event with exact time known, and we'll record it as a 1 in new column we call sensor. In the time column, 1.2 will be recorded. This is a summary of all what I explained you before, where I specifically tell you exactly what will be, how you are going to define your data set, and after how you are going to define the likelihood. In the patient B goes to the clinic 2 months after starting the medicine and is asked if he had an attack during the 2 months. The patient, remember, he got 1 attack and that's it. No exact time is provided, but only the fact that he got 1 attack. This is both a count response, and we can use the event statement for it, which is basically the statement that it's linked to count time to event. But instead of putting a 1, we put a -1 to basically not be confused with the 1 that means exactly at that time I got an event. The patient C comes after 2 months and tells the doctor he didn't have any attacks. Again, I just explained you that. This is called white sensor, as we stop following the patient and do not know when he will have an attack, but only that he did not get any during the first 60 days. The sensor column will have a 0 recorded. The time column will show 60 days. Okay, and now we have basically repetition of very similar case. Patient D comes after 2 months and tells the doctor he had an attack between day 7 and day 10. That's what he's remembered. It means that he didn't have anything in the first 7 days. And then between 7 and 10 days, 1 attack. This can be handled either with count data or time to event data. In both cases, you need to have the time column with both values 7 and 10. And obviously 0. 0, nothing happened, you put sensor of 0. For count data, when time is equal to 7, you need to put a 0 to reflect that you didn't have anything from day 0 to day 7. And when time is equal to 10, you put a 1. That's if you use the count data. If you use the time to event data, it's very similar, except that you're going to put a -1 and day 10. Then when time is equal to 7, you need to put a 0 to reflect that no event occurred between 0 and 7 days. And then on day 10, you put just -1. Fifth case, patient E comes after 2 months and tells the doctor he had at least 1 attack on the first week after starting medication. In the PML, the Phoenix and LME, to differentiate between basically the exact 1 event occurring where we put a 1, here are going to put a 2, which means that you basically tell the program when the sensor will be equal to, it means that basically you had at least 1 attack. In other words, either 1, 2, 3, 4, 5, etc. That's basically what you need to know. And again, the 6 scenario is exactly like the scenario that we are talking about when we're talking about count data, then I don't need to repeat that. Then the last things that we need is basically how to define the likelihood, because when you are going to have data, then again, depending on the kind of time to event that you have, and again, count data enter into time to event, you will need just to write what is the likelihood, okay? Now, then this leads her to the concept of survival distribution. The survival distribution is telling you the following. At the beginning, everybody is alive, okay? And the survival distribution is equal to 1 because the probability to survive up to t equals 0 is equal to 1 because nobody died at the beginning or nobody get any, and we make the assumption that when you start the trial, nobody get an event. Then the probability not to get an event, which is the survival distribution, is equal to 1. It appears that at each moment, the patient can have an event. And once it got the event, we record in the sensor column the value 1, if indeed we know the exact time at which it got the event. Now, there is a probability we are interested in, which the probability not to get an event or to survive up to time t equal t. And this is called the survival probability, and we call it S. The good news is that, and that's what you need to know, like count data, For time to event, the only things that you need to define is the hazard rate. Because the concept of count data or time to event is exactly the same concept. In count data, something happened between T0 and T1, between 0 and 2 months. In time to event, the case that you know exactly when it happened, something happened, but you know exactly when it happened. But both are linked to the same hidden process that it's continued, which is the hazard rate. The difference is that when you use time to event, there's a concept instead of integrating the hazard rate and then assuming that the cumulative hazard rate is linked to a Poisson distribution, here we are going to link the hazard rate with the survival distribution. In fact, it appears, and again, this is just for you to know what we are talking about, but in practice, you just really need to define the hazard rate. It appears that you start with the probability not to get an event equal to 1, and then basically we assume that you have an exponential decrease for the survival distribution, where basically the exponent component is basically h, which is the hazard rate. In other words, the rate at which the probability not to get an event basically decrease is equal to minus h multiplied by s. Now, if I'm looking at the survival distribution at a specific time, what's the meaning? If, for example, I'm telling you that the s is equal to 0.5 at t equal 5, what does that mean? It means that the probability to survive up to 5 days is equal to 50%. Obviously, every time that I'm going up with the time, there's more probability that to basically get the event. Then the probability, the survival probability not to get an event, at the beginning it's large, and at the end, basically, it starts to be low. And it's basically an exponential decrease, okay? And it depends on h. Now, if h is constant, then it's really like a one compartment model. It's like a one compartment model IV bolus exponential decrease where h is constant. Then if we now want to define what is the survival distribution as a function of the hazard rate, this is very easy. I have ds dt equal minus h multiplied by s. I divide by s here. I'm putting the s on the other side and the dt on the right side. And I integrate. And you get integral of ds divided by s is equal to integral minus h dt. And I know that the integral of ds divided by s is the logarithm. Again, that's to remind you some calculus, okay? If you don't know that, it's not really critical. Then basically, when you have the integral with boundaries and the integral of ds divided by s is logarithm, we have your boundaries equal to logarithm at that time, t equal t minus the logarithm at the original time. And because at the survival distribution at t equals 0 equal to 1, ln 1 is equal to 0, and then you are left with the integral of t equals 0 to t of minus h dt. But this is the logarithm. Then if you want to get s, you just need to put exponent operator to cancel the logarithm. And then you get s equal to exponent t equals 0 to t equal t of minus h dt. Why I'm telling you that? I'm telling you that because the program is going to do that for you. But you can see that if you know h and you know the times 0 and t, then the program can calculate automatically that survival distribution. Now, why do we need the survival distribution in the H to calculate the likelihood? That's just basically because of the following. Let's just look just at that's basically my last slide. I'm just going to take 3 examples, 3 scenarios. If I know the exact time to event, what is the likelihood? And again, why do you need the likelihood? Because the likelihood, that's something that you need to write down unless in R and LME is going to give you that option automatically. I don't know exactly what we have R and LME. Suppose that you know exactly when the time to event occurs. Then you will need to calculate S. In other words, or either the program is going to calculate this for you. Again, I don't know exactly what you have in R and LME. You will need to calculate S, and then you will need to calculate H at that time. If you know S at that time and H at that time, that's the likelihood associated with you knowing the exact time of the event. If you have an interval sensor, one event between previous and new event observation, then the likelihood basically is going to use the count data likelihood, because it's basically count data. Then again, is going to integrate the hazard rate from the previous observation to the new observation. Is going to associate that cumulative hazard to the mean of a Poisson distribution. Then then he's going to say, okay, now I got one event between the previous and the new time. Then what's the probability to get one event if my mean of the Poisson is equal to something, let's say 0.8. And that will be your likelihood. And the last scenario, which is the last scenario that is important, is that if the patient is telling you that he got at least one event, which means either 1, 2, 3, 4, 5, etc., let's say asthma attack, it means that the probability to get 0 event is equal to 1 minus basically that probability. But I know that exactly S is the probability to survive, which means not to getting any event. Then in other words, 1 minus S will be basically the likelihood for the last scenario. Then if I summarize the time to event, it's very easy. You will need to define the hazard rate. You will need to calculate the survival distribution at the time point at which you have your observation. And again, I don't know what RNME is going to provide for you. If not, you have all the mathematical background that allow you to do that. And then depending on the 3 kind of time to event that you have, that one include count data, you need to write the likelihood. Once you write the likelihood, everything is done, because you just need to know the likelihood associated to one specific observation. And then since you have only 3 cases, then it will be either S multiplied by H, either the Poisson distribution, or 1 minus S. If we summarize all what we did today, we talk about a very more complicated time of data, because we really don't see a lot. And again, hopefully I will be involved also with helping students once you have real data. I mean, I know Phoenix and LME because I'm one of the persons that have been involved in the development of the program, but I'm not involved with RNLME, but both are going to use the same code, and hopefully I will be able to help you. Then when you have continuous data, it's very easy. We see what we have, and then we can handle that because of goodness of fit, we have visual predictive checks, we have a lot of things that we can do. Then we enter a completely new world that many people do not know about, and that's really my expertise. It's really dealing with this kind of data. And then we have 3 kinds of data that we need to consider: categorical response, count data, and time to event. Categorical response, the rule of addition and multiplication do not apply. And then we have like pain level or disability level. We need to compute the probability to get a specific level, and I explain you how to do that. Then we have the count data, where the rule of addition and multiplication apply, but what we observe, it's really an integer. It can be either 0, 1, 2, 3, 4, 5, but cannot be 1.5, etc. For count data, the way to define the likelihood is to go through the hazard rate that tell you the number of events per unit of time. You integrate the hazard rate to get the cumulative hazard. The cumulative hazard is associated with the mean of a Poisson distribution. And your likelihood is the probability, given that mean of the Poisson distribution, to have observed the number of events that you observed. That's the likelihood. Then we go to the time to event. We have 3 cases: exact time to event. Then we need to define the survival distribution, the hazard rate. The product is the likelihood. Interval sensors like count data. And then the third scenario is basically the time to event, is that you know that you get at least one event. And then it's equal to 1 minus the survival distribution. Then now we are done with my part, and hopefully it will help you. If it doesn't help you now, it's going to help you later. What I hope that will happen is that when you are going to deal with this kind of data with the software, then all what I've explained you for these 3 or 4 sessions will appear to be hopefully useful. Thank you very much. If we have questions, I will be happy at least to try to answer the question.
Thank you, Serge. Great workshop today. again, if you have questions, you can raise your hand, and or I can unmute you so you can ask questions of Serge. Serge, I would also really appreciate if you can go over the homework questions that we had provided to the participants after the day 2 of the workshop.
You mean the PD homework?
Yes.
Okay. Okay, do you want me to do, do you see my screen?
Yes, we can see.
Do you want me to do that now? Because I want to give time to the students to work on it, but I can explain maybe the questions.
Sure. So if you can, I mean, I completely agree with you. We are not going to be going over the answers. We will just discuss what needs to be done.
Okay. Okay, I get it. Okay, then let's just me explain you a little bit what we are talking about here. It's really a practical application of what we learned about indirect response model. Then you will need to work a little bit on that. Let me show you first the data set. And you can see here, and this will familiarize yourself at least with the format. Again, with RNLME, I guess that the format will be quite similar. Usually what you are going to see, it's a column for the ID, which is the patient number, then a column with the time, and then in column with the PK observation, and usually we put units, then in column with the PD observation, and then I add here as a strata the dosing level. Here we have 1,000, 10,000, and 100,000. Then you can see here we are talking about a drug that is given as an infusion. Then either you give the duration of the infusion or you give the rate of the infusion. You can see microgram per hour. And every time that you see a number here, it means that at that time, you give that dose. If you give a dose with a certain rate, you see 10 microgram per hour, and you understand that if you know the rate and you know the dose, then you can know the duration of the infusion. Again, that's something that we're going to do. Then these are basically are the data, okay? Then it's a PK PD model. Now, what I'm asking you to do is the following. COPS and EOPS are the observed PK and PD response respectively. And I just show you the PK PD data set. You can see it also. And here's the dosing regimen. The PK PD parameter as well as the dosing regimen are shown below. Now, I'm a nice guy, then I'm going to give you basically the parameters. The PK model is a one compartment model, which means that you have only volume and clearance. And also I'm telling you the value 100 for volume, 5 for clearance. Okay, and remember we are talking about an infusion, and there's no random effect. Okay, and each of the patients share the same parameter. Now, the PD model is an indirect response model that has K in is the natural rate of production of the biomarker, the response. K out is the first order elimination of the biomarker. And Emax is basically a factor by which basically is going to increase your response. EC50 is the concentration of the drug that is going to lead to half of the maximum Emax. STDV0, it is basically the coefficient of variation for your PK model that is assumed to be multiplicative. And the PD model is assumed to be additive. I want to remind you that in many situations, we assume multiplicative error for PK and additive error for PD because the PK basically span over a huge range of values. You know, we have usually you have very low levels up to very high levels. And then you need to consider that the variance of the observation, what's called the error model, basically change because you go from low to high concentration. On the other hand, when you have a PD model, most of the time it spans over a quite small range of value. Let's say it's going from 50 to 100, or even 10 to 100. But it's not huge range, and usually additive works quite well. Okay? Here it's the case. The dosing regimen, the cohort, which is basically patient 1, it's a dosing of 1,000, and you can see that from the data set. You can see 1,000 here. Okay, I'm just explaining what you have here. Then the first cohort, and again, each cohort, I gave you the average value that each cohort corresponding to one average patient is getting a dose of 1,000 microgram at a rate of 10 microgram per hour. Okay, and it starts at t equals 0, and then the total amount for that patient is 1,000 microgram. The second cohort, it's 10,000. The third cohort is 100,000. Okay, you can see that this allows me to define what is called the dose-response relationship, hopefully. TVP, where P is either V, CM, Kn, K, etc., stand for the typical value of the parameter P. Since there are no random effect, the average that are given here, then P is equal to TVP. Okay, and basically there's no random effect. Then the only parameter that you have is volume clearance, natural production of the biomarker, first order elimination, the Emax, the EC50, and that's it. Okay. Now I'm going to write now the equation for the one compartment model with an infusion that stopped after a certain duration. And this is called a differential equation. A1 is the amount in the central compartment, it's the one compartment model. Then you have D1, dA1 dt is equal to the rate. And again, you know the rate. I gave you the rate for the 3 cases. Okay. Multiply by t less than the duration. When I multiply by t less than duration, what I mean is that as long as the time is less than the duration of the infusion, and again, you can know what's the duration of the infusion because you know the rate and you know the dose. Okay, you are going to do that. That's a part of the homework. Then you know the duration. Then you know that the rate is going to be that rate as long as the infusion is there. Then the rate, then basically the input of the drug will be only for a certain duration, but the elimination is the first order, and it's equal to minus CL multiplied by the predicted concentration, which is minus CL multiplied by C. And again, the duration is the dosing divided by the weight, and you know the dosing, and you know the rate. And I gave you the answer, then you know it's the duration. A1 is the amount in the central compartment, and C is the predicted concentration in that compartment, which is the compartment where you observe your data. Then C is equal to A1 divided by V. And again, rate is the rate of infusion. Even infusion is given until T equal duration. T less than duration is equal to 1 for 0 T duration, and 0 is the right. In other words, this is basically, it's called delta function, that T less than duration is equal to 1 as long as your infusion is active, and then 0. In other words, that term will disappear once the infusion is finished, and you are left only with a first order elimination. Now, the equation for the PD part, okay, you can see that ddt, which is the change in the response over time, depend on 2 things: the production of the biomarker and the elimination of the biomarker. The production of biomarker without a drug is called Kn. And then you have an effect of the drug. You are going to tell me what kind of effect. That's part of the question. You can see that basically I have 1 plus Emax multiplied by C plus EC50. And by the way, I gave you what is Emax, and the TV is not relevant because there's no random effect. And remember that you know what is Emax, you know what is EC50, okay? And maybe you will know what is C. That's a part of the question. I assume that before I'm giving the drug, we are at steady state. And E is equal to K in divided by K out, and we learn that together. And that's basically the initial condition before I'm giving the drug. Then who knows what will happen when I'm giving the drug? Something will happen. It's my response. It's going to go up or go down, I don't know. That's basically you're going to tell me. Then here are the 7 questions. What can you tell me about both the PK and the PD model? I already answered almost, but again, I want you to explain what kind of PK model we have here, what kind of PD model we have here, okay? Then I'm telling you, okay, can you plot, please, the observed PD response versus the PK response for the 3 different dosing cohorts? Again, I gave you the data, and I gave you an Excel spreadsheet, and you can use any software that you want just to plot data, okay? And then I'm asking you, do we see hysteresis? And then remember that we talk about the indirect response model, and we learned about hysteresis. Because there's a delay between PK and PD, and I'm not going to tell you more than that. Then just you are going to plot the data. Do we see hysteresis or not? If so, is it clockwise or counterclockwise, and why? In other words, when you are going to plot, when you are going to plot the PD versus the PK, and for each data point you are going to put the time, okay? Then you can see basically when the time goes up, what do you see with the hysteresis, if there's indeed an hysteresis? Is it clockwise or counterclockwise, and why? That's basically the question. Based on the model and the above PK/PD parameters that you know, and there's no random effect, what should be the predicted steady state level for the PK response for the 3 dosing cohort, assuming the infusion would not stop? Okay. If I'm giving an infusion, and the infusion doesn't stop, then what will happen? Again, I cannot give you all the answer. And again, this doesn't stop. In other words, this doesn't stop, it continues. What will happen is that basically, at some point, the input, the infusion input will be equal to basically the first order of elimination. When you reach that, we reach what is called steady state. What does that mean, steady state? Steady states mean that basically dA1 dt equals 0. And now I'm not going to give you more than that. Then if I would not stop the infusion, then basically at some point there will not be any net change in the amount of the drug in the central compartment, and I will reach steady state. Since you know the rate and you know the clearance, then you should be able to know what would be the concentration at steady state, okay? And that's the question. What should be the predicted steady state level for the PK response for the 3 dosing cohort, assuming the infusion will stop? And then I'm asking you, did we reach approximately, if we neglect the data noise because you have noise in the data, steady state level based on observed data? Then what's the question here? If, for example, the infusion would be quite short, then you understand that basically if it's so short, then maybe I will not reach steady state in that short time. Then you can look at the data and look, okay, when I'm stopping the infusion, what was my level? And then look basically if this level is approximately the level that I just predicted for the PK, okay? That was basically the question. Then the next question is, what is the maximum factor by which the PD can be increased, assuming the infusion wouldn't stop? And did we reach approximately that maximum at the end of infusion? And if so, for what dose level? What is the approximate percent of that maximum can be seen at the 3 dosing level at the end of infusion? Then what the heck is that? What I'm talking about here is that basically we have a model, it's the PD model, okay? And then if I would continue the infusion forever, I would reach steady state. And at some point, if I'm waiting forever, I will reach steady state for ddt because I do not stop the infusion. And this is equal to 0. Then if I know that ddt equal to 0, and I know the steady state level for C, then you are going to calculate what would be my new level for the PD response, okay? And then you will know basically what is the maximum factor by which the PD can be increased. In other words, at the beginning, it's K by K out. And if I do not stop the infusion, what will happen at the new steady state if I do not stop the infusion? That's basically the question. Then I say, okay, now I stop the infusion. Then I say, okay, now let's look at the end of the infusion, what is the observed level of my PD response? And I'm asking, do you think that we reach for the 3 dosing basically steady state? And that was basically the question. Since I know what's the maximum that I can get increase of my PD response, I'm asking as the last question, what is the approximate percent of that maximum can be seen at the 3-dose level at the end of the infusion. You are going to calculate what's the maximum increase I can get. Then you are going to look at the data and look basically what's by how much relative to the maximum I improve my PD response. And the last question is basically I gave you one model that show me, I don't know, increase or decrease in response. You are going to tell me about it. What other PD model could give us similar PD profiles? And this is very important because that's why you need a clinical pharmacologist that I'm not. It's when you have data, maybe 2 different processes could give me the same profile for my PD response. And what I'm asking is what other type of similar equation could give me very similar response? And that's basically the last questions. And I'm giving you quite time to do all that. And I think that this will help you when you are going to deal with real data. Okay, that's it.
Thank you, Serge. And there was also another homework assignment that we had shared, which was the likelihood.
Yes, but the likelihood I told not to do anything about it is because it's way more complicated than no need to do anything about the likelihood. I will try to add some question this week about categorical count data and time to data, and although it's quite difficult because I don't have real data and I don't have the software I need to think about, but I will try to do that. So I think about the likelihood, nothing to do about it.
Sure. So also wanted to mention to all the participants that you should be getting access to RS and LME in the next few days. And I wanted to check with Keith if you want to mention anything about can they be can the participants use the RS and LME to answer any of these questions? Keith, if you are online and if you would like to comment on it, please.
Am I unmuted?
Yes, Keith.
Yeah, so of course, it is possible to answer some of these questions with RS and LME. Unfortunately, I don't think any of the participants have it installed yet. So I know Anna is going to be organizing that. And yeah, certainly once we have that installed, we can be using our SNLME to answer some of these questions. Yeah.
Thank you, Keith. So I think there was one question that I can see in the chat box, which says that will there be additional homework based on today's topic? So I think Serge has already answered the question for you that Serge is going to be looking into if there is an assignment that he can put together, which may not be, again, we are still waiting to get access to RS and LME, but I also do want all of you to be aware that many of these questions can be answered just by looking at the data and plotting the data. Again, I would strongly urge you to put on your clinical pharmacologist hat and address these questions, because pharmacometrics or mathematical modeling is an extension of your clinical pharmacology understanding. Again, the data speaks for itself. You can practically use Excel to do many of these, address many of these questions, especially when it comes to making a plot. And these questions are more related to the logic rather than how you write a program. And me being a clinical pharmacologist with a pharmacometrics background, I personally would request you to address these questions, erring more on the clinical pharmacology side, because we will be working through the modeling pieces in the next modules. And I wanted to check if there are any questions that the participants have from what Dr. Gozi covered this morning. And again, you will be getting access to the slide decks as well as this lecture, which is being recorded. We will be sharing, putting this on our YouTube channel. If you have a question and would like to talk to Dr. Gozi, please raise your hand and one of us will be able to unmute you.
Dr. Gozi, we have one question in the chat panel. I can just read it out for you. So we have a question from Vishal. So it's a scenario like the probability of an event may increase with treatment time, that is from the first month to the second month and to the third. So how to get a factor instead of calculating the probability every month? If I get it right, so is there like what is the factor by which the probability increases every month rather than calculating the probability for every month?
Are you talking about time to event?
There is no specification on what kind of model they want to. It just says probability of event.
Yeah, he's talking about probability. Then I'm not sure I understand the question. Let me explain again the way it's working. Maybe what he's talking about is basically time effect that can affect the probability to get an event. Then when I was talking about basically the hazard rate, the hazard rate can include either a drug effect or sometimes also a time effect. Then if you see that basically the hazard rate has a time effect that it's independent of the drug effect, then you can basically define this through your hazard rate and say that UH is equal to H0, which is your initial hazard rate, multiplied by 1 plus, and then you put basically a time effect, multiplied by 1 plus, and then you put a drug effect. And that it's done many times when you have also placebo data, and then you see that basically your hazard rate changes with time, even if you don't have a drug. Then again, to answer to that question, if I understood the question correctly, if you know that basically the probability to get an event increase with time, you can always define this through your hazard rate by adding a time component for your hazard rate. But again, I would need more specifics about exactly the kind of problems. But
so Vishal, if you would like to elaborate on your question, please raise your hand and we would be able to unmute you.
Again, I want to know if we are talking about time to event. I mean, I guess so. Or count data is the same thing. Somebody raised his hand. Vishal Pendarka.
Okay.
Hi, Gozi. Vishal here.
Hi.
So it was about the cardiac events, the slide where you discuss the cardiac events on each month. So with time, with time and the treatment, the cardiac events, the likelihood of having cardiac events would increase. So how do you, factor that? So that was the question. So these are basically count data, not the.
Okay, but that's the same thing because if you talk, I mean, you see my screen? Yeah, I guess so.
Yes.
And then basically when count data or time to events are based on the same principle, is that every factor that you want to account for must be put, you see the count data? Then you need to define just everything. You see here, the H equal A0 cover 1 plus C by C plus C50. That's basically, you assume there's no time component, but only an exposure component. And that the time, it's indirectly related because the exposure changes with time. Now, sometimes what can happen is that you can see that even for placebo data, you can have the number of events that increase with time. And you could have basically, I can even write it here. You can write it 1 minus 1 plus a function of time. That would reflect basically, again, whatever function you have here, like an exponential decrease or increase or whatever. And this could basically account for it. But again, when I gave you the example, it was not really related to any specific kind of data. I'm just telling you that whatever you can have with your data, you can put a non-exposure effect, which is basically the hazard rate, that here is a constant. But instead of having constant, you could have this changing with time, even if you don't have basically exposure data. But when I gave you the example, here, I don't know exactly what was the example. What's happened in first month and second month, that was completely arbitrary. It was not taken from real data. When you get real data, then usually the strategy is to look first, okay, do I have placebo data? Okay. And if you see that you have placebo data, and let's say the first scenario, you see that in the first month you have basically 1 count. Second month you have 2 counts. Third month you have 0 count. Fourth month you have 2 counts. Fifth month you have 1 count. If you see that there's no trend, that the average number of counts really don't change with time, then you don't need to add any component. Now, what maybe you specifically talk about is what's happening is in the first month I got, let's say, 4 counts. Second month I get 8 counts. Third month I'm getting 12 counts, etc. Then you need to distinguish: do I get more counts because of the drug, or not because of the drug? And the way to answer that is using the modeling. First to look, do I have placebo data? If you see that you got an increased number of counts with time independently, even if you don't have exposure for placebo, then you need to change your H0 and add the time component. If the reason for increasing the number of counts is just due to the increase in the exposure, then in that case, maybe you don't have a time component, and you can just use this kind of equation. But again, I just gave you the concept. I didn't talk about specific case. I have many cases, but once I will see the software, because I have no clue how the software looks, then once I will have more information about the software, then maybe I will be able to explain more with real data how to handle that. Where I will be able to help you, it's really with, I understand that the software is based on the Phoenix modeling language, and I will be able to help you with the Phoenix language, but not more than that.
Thank you, Serge. Any other questions for Dr. Gozzi here? We have about 15 more minutes, and I wanted to check that you are powerfully set up to start working on the homework assignments. And of course, between today and next week, I would strongly encourage you to meet with your groups and start working on the homework assignments. And when we meet next week, that would be the last lecture by Dr. Gozzi. So I would encourage you to bring any questions that you have in the module 1 that Dr. Gozzi has covered. Do go over all the slide decks, go over the homework assignments. And again, I'm a strong believer that there is no question which is a stupid question or a wrong question. All questions are questions, and that's all they are. So I don't see any movement either on the chat window or anybody raising hand here. So I see a question which has come up asking about when would this video be posted on YouTube. We will try to get this done in the next, I would say, day or two. But yeah, you should have access to the YouTube video as soon as possible. And I'm aware that we are stepping into a weekend, so which might be that you will have more time to work on homework assignments during the weekends. So we will try to get this done as soon as possible, so you have access to it. Any other questions? If not, we will be terminating, closing the workshop for today. And again, a workshop of this size is not possible without all the contributions from our team members of Project Dontabhaktuni, and of course, our sponsors, which is Pharmapro Consulting and Certara. Thank you to all of you for being here and sharing this knowledge with us about Pharmacometrics. And we look forward to seeing you in our workshop again next Friday. If anything comes up, and I know that some of you have had some technical issues with regards to making the payments, etc. So if you would like to talk to us, the Project Dontabhaktuni team, please stay back. Myself and all of our Project Dontabhaktuni team members will be available online after we have closed the workshop as well to help address any questions, concerns that you have. Again, thank you, Dr. Gozi, for making the time and being here and sharing your knowledge about Pharmacometrics. And we look forward to seeing you again next week.
Okay, my pleasure. Okay, thank you very much. And I will try to find some questions that are relevant for categorical content time driven, although it's really more difficult because we don't have the software that we can use. But I will try to maybe to find some questions that are relevant. Okay.
Thank you, Serge.
Okay. Bye-bye. Thank you very much. Bye-bye. Have a nice weekend.
Yeah.
Bye.